Hey guys, welcome back to ITower. Today we're doing something really exciting, creating our own custom hooks system in vanilla JavaScript, inspired by React hooks but built completely from scratch. You might wonder, why do this when React already has hooks? Well, building them yourself helps you understand core ideas like state management, function composition, and reusable logic. Whether you're working on vanilla.js projects or just want to see what's happening under the hood of React, this is going to be super valuable. The skills you'll gain today go way beyond just writing code. You'll learn how to design intuitive APIs, manage state without frameworks, and build clean, reusable abstractions, the kind of thinking that separates juniors from seniors. These concepts apply everywhere in modern web development, not just in React. Understanding hooks at this level makes you better at debugging React applications, designing cleaner abstractions, and making informed decisions about state management. This knowledge is practical too. You can apply it when building custom tools, internal frameworks, or any situation where you need stateful behavior without relying on a full framework. This kind of architectural understanding is what employers look for in senior developers. Anyone can use a framework's API, but understanding why the API is designed that way, what problems it solves, and how to implement similar patterns yourself, that's the difference maker. You can apply these concepts in job interviews when discussing state management, in architecture discussions when designing new features, or in code reviews when evaluating different approaches to solving problems. Before we dive in, a quick favor. If you enjoyed these deep technical breakdowns, please like and subscribe. It really helps the channel grow and reach more developers who love learning how things work under the hood. Your support helps us keep creating detailed explorations and lets other developers find content beyond surface-level tutorials. A custom hook in vanilla JavaScript is simply a design pattern that lets you extract and reuse stateful logic from your code. Just like React's useState or useEffect, these hooks manage state and behavior but can be built without any framework. The idea is to create small dedicated functions that handle specific functionality like form validation, API calls, or window resize tracking, and expose a clean, simple interface. This separation of concerns makes your code easier to test, maintain, and reuse across your application. We use this pattern instead of regular functions or classes because hooks are both composable and stateful. Unlike regular functions that just return a value, hooks can remember state between calls and provide ways to update it. This makes them perfect for reusable logic that needs to persist over time. While classes can handle similar behavior, hooks offer a cleaner, more functional approach that keeps your code predictable, easy to maintain, and less error-prone. The hook pattern is used extensively throughout modern JavaScript development. You'll see similar patterns in Vue's composition API, in Svelte reactive declarations, and in countless libraries and tools. Understanding the underlying mechanics means you can pick up new tools faster and use them more effectively because you understand the core concepts they're all built on. Let's start building our hook system from the ground up. We need to create a mechanism that can track state across multiple function calls, which is the fundamental challenge. In React, this is handled by the framework's internal fiber architecture, but we are going to build a simpler version that demonstrates the core concepts. We'll create a state management system that keeps track of which hook is currently being called and maintains an array of state values. First, we need to set up our global state tracking. We're going to create a variable called currentComponent that will hold the state for whatever component or function is currently executing. This is necessary because we need to know which piece of state belongs to which function call. This variable acts as a pointer to tell our hook system which component state we are currently working with. When we call a function that uses hooks, we'll set this to point to that function's state container, and when the function finishes executing, we'll clear it. It's a simple but effective way to maintain context. Next, we need a variable to track which hook we're currently on within a component. Since a single function might call multiple hooks, we need to keep track of the order. We'll call this currentHookIndex. This index is essential because it links each hook call to its specific state value. Every time a hook runs, the index increases, and when we re-render, it resets to 0 to realign all hooks correctly. That's why hooks can be called conditionally. Their order must stay the same across renders, just like in React. Now let's create the actual useState hook. this is the foundation of our system. We'll create a function called useState that takes an initial value and returns an array containing the current state value and a function to update it. We're naming this useState to match React's convention, which makes it immediately familiar to anyone who's used React. The function accepts an initial value parameter, which is what the state will be set to the first time this hook is called. This could be a number, string, object, array, or any JavaScript value. Inside the function, we first need to get reference to the current component state array. We'll access the hooks array from current component. This line accesses the array that stores all hook states for the current component. Each component has its own hooks array, allowing multiple components to use the same hooks independently. The array acts as a list where each index matches a specific hook call within that component. Now we need to capture which hook call this is. We'll store the current index value before we increment it for the next hook. We store the current index in a local variable before incrementing the global counter, so this hook instance can remember its exact position. That's how each useState call keeps track of its own state, even when multiple hooks are used in the same component. The hook index acts as a unique reference for that specific instance. Now here's something really important that we need to do. We also need to capture the render function right now, while current component is still set. Why? Because after the component finishes rendering, current component will be set back to null. But our setState function needs to trigger re-renders, and it might be called much later, long after the component has finished its initial render. So we capture the render function in a closure. This line creates a reference to the render function that will survive even after current component is cleared. It's captured in a closure of our useState function, so every setState we create will have access to the correct render function. This is a critical part of how closures enable stateful behavior in JavaScript. Without this capture, we'd get a null reference error when trying to trigger re-renders, because current component would already be cleared by the time setState is called. Now, let's increment the global hook index, so the next hook call gets a different position. This guarantees that each new hook call in the same component gets the next position in the hooks array. Because hooks are always called in the same order on every render, this indexing system keeps each hook linked to its correct state, ensuring everything stays consistent and predictable. Next, we need to check if this hook already has state value from a previous render, or if this is the first time it's being called. We'll check if the hooks array has a value at our current index position. This condition checks whether we store anything at this position yet. If it's undefined, that means this is the first render and we need to initialize the state with the initial value that was passed in. If it's not undefined, that means we've rendered before and we should use the existing state value instead of resetting it. If this is a first render, we'll initialize the state with the initial value provided. This sets up the state for the first time. The hooks array now has our initial value stored at this hooks designated index. On subsequent renders, this condition will be false, because the value will already exist, so we'll skip this initialization and use whatever value is currently stored there. Now, we need to create a setter function that will allow us to update this state value. We'll create a function called setState. We use an arrow function stored in a const to create a closure around both the hook index variable and the render_fn we captured earlier. This allows each setState function to remember which hook it belongs to and how to trigger a re-render. The new value parameter represents the value the user provides when updating the state. Inside setState, we update the hooks array at this hook-specific index with a new value. This is where the actual state update happens. We directly modify the hooks array at the position that belongs to this specific hook. Because we captured hook index in a closure, this setState function will always update the correct position in the array, even if it's called much later or from a different context. After updating the state, we need to trigger re-render of the component so the UI can reflect the new state. We'll call the render function that we captured earlier in our closure. Here's where that captured render_fn comes into play. Even though current component is now null, because the component finished rendering, we still have access to the render function through our closure. This is the beauty of JavaScript closures. They preserve access to variables from their creation context. When we call render_fn, it will re-execute the component function with the updated state. and the cycle continues. Finally, we return an array containing the current state value and the setState function. We're returning an array so users can destructure it with whatever variable names they want, just like in React. The first element is the current state value from the hooks array, and the second element is the setState function we just created. This API design lets developers write code like const count, setCount equals useState 0, which is clean and intuitive. Now we need to create a component system that can use our hooks. Let's create a function called createComponent that takes a component function and returns a render function. This function is our component factory. It takes a function that represents a component, which is just any function that might call hooks, and wraps it with the necessary state management infrastructure. The component defend parameter is what the developer writes. It's their actual component logic. We need to create a state container for this component. This object will hold the hooks array and any other component-specific data. The component object has three properties. The hooks array is where all the state values for this component's useState calls will be stored. The fn property holds a reference to the actual component function, so we can call it during renders. And the render property starts as null but will be filled in next. This is crucial for allowing our useState hook to access the render function later. Now we'll create the render function that will execute the component and handle the hook system properly. The render function runs the component and manages hook tracking. Whenever we display or update the component, this function sets up the hook context, executes the component and handles cleanup afterward. First, we need to set the global current component to point to this component state container. By setting current component to our component object, we are telling the hook system which component state to work with. Any hook calls that happen while the component function is executing will now correctly interact with this component's hooks array. We also need to reset the hook index to 0 before we start rendering. Resetting the index ensures that the first hook call in the component will access index 0, the second will access index 1, and so on. This reset is crucial because every render needs to process hooks in the same order. If we didn't reset this, subsequent renders would try to access the wrong positions in the hooks array. Now we execute the component function, which will call any hooks it uses. This is where it all comes together. When component fn runs, it calls useState or other hooks, and because current component is set and current hook index is reset, each hook accesses the correct state. The result variable captures whatever the component returns, whether it's a virtual DOM, a string, or any other output. After the component finishes executing, we should clean up by setting current component back to null. This cleanup is good practice to prevent accidental state leaks. Once the component has finished rendering, there's no reason for the global current component pointer to keep referencing this component. Setting it to null makes it clear that we're not currently in a render cycle. This is why we needed to capture the render function earlier in useState, because by the time setState is called, current component will be null. Finally, we return the result that the component function produced. We're returning whatever the component generated so the caller can use it, whether that's to insert it into the DOM, log it, or do anything else. The render function serves as a clean interface between our hook system and the actual component output. Before we return the render function, we need to store it in the component object, so useState can access it. This is the final piece of the puzzle. By storing the render function in the component object, we make it accessible to useState when it creates setState functions. Remember, useState captures the render property from current component in a closure, so this needs to be set before any hooks are called. This connection is what allows state updates to trigger re-renders. Now we return the render function, so the user can call it whenever they want to render the component. By returning the render function, we give the user control over when the component executes. They might call it immediately, call it in response to user events, or set it up on a timer. The render function carries all the state management logic with it through closure, so it's completely self-contained. Let's create a practical example to demonstrate how this all works. We'll build a simple counter component that uses our custom useState hook. This is our component function. It's just a regular JavaScript function, but because we'll pass it to create component, it will gain the ability to use hooks and maintain state across multiple renders. Inside the component, we'll call useState to create a piece of state for our counter value. We'll initialize it to 0. We destructure the array from useState into count and setCount. Count holds the current value, starting at 0, and setCount is a function to update it. This line provides persistent state management without classes or complex setup. Let's return an object that represents our component's output and include some methods to interact with it. We are returning an object with 3 methods. The render method logs the current count value to the console, which lets us see the state. The increment method calls setCount with count plus 1, which will update the state and trigger error render. The decrement method does the opposite, subtracting 1 from the count. This API design gives us a simple way to interact with our stateful component. Now let's move to testing and see our custom hook system in action. Testing is crucial because it proves our implementation works correctly and handles state updates as expected. We need to verify that state persists across renders, that updates trigger re-renders properly, and that our closures are capturing the right values. We need to create an instance of our counter component using the createComponent function. By passing our counter function to createComponent, we get back a render function that's bound to a specific instance of the component with its own state. This counter variable is now a function we can call to render the component, and it will maintain its state between calls. Let's call the render function to initialize the component and get our first render result. This first call executes the counter function. Inside, useState is called for the first time, which initializes the state to 0 and returns that value along with the setCount function. The counter function returns its object with the render, increment and decrement methods, and we capture that in render1. Now let's display the initial state by calling the render method. When we call this, we see count0 logged to the console. This confirms that our useState hook correctly initialized the state with the initial value we provided, and that the component can access that state. Let's increment the counter by calling the increment method. When this executes, it calls setCount with count plus 1, which updates the hooks array to store 1 instead of 0. The setState function then automatically calls renderFN, which re-executes the counter function. The second time counter runs, useState sees that hooks at index 0 already has a value, so instead of using the initial value 0, it returns the stored value 1. This is the core of how state persists across renders. Since increment triggered a re-render, we need to capture the new render result. Let's render again to get the updated output. Now when we call render on this new result, we see count1 in the console. The state has persisted and updated correctly. Our hook system successfully maintained the counter value between renders. Let's test incrementing multiple times to make sure the state continues to update properly. We will call increment on the latest render result. This displays count2 in the console. Each increment call updates the state, triggers a re-render, and the new render correctly reflects the updated state. The hook system is tracking state changes across multiple render cycles, exactly as we intended. Now let's test the decrement functionality to make sure state can decrease as well as increase. We see count1 logged now. The decrement method called setCount with count minus 1, which updated the state from 2 back down to 1, and the render reflects this change. This confirms that our setState function works correctly for any kind of state update, not just increments. Our hook system is fully functional and handles state management exactly like React's hooks do. So today, we've built a working hook system in vanilla JavaScript, exploring the core concepts behind React hooks and similar state management patterns. You've seen how to track state across function calls using closures and arrays, how to create a component system that supports reusable stateful logic, and how to design APIs that are intuitive and developer-friendly. Understanding hooks at this level not only helps you grasp how modern frameworks work under the hood, but also makes you better at debugging React applications, designing cleaner abstractions, and making informed decisions about state management. This knowledge is incredibly practical. You can apply it when building custom tools, internal frameworks, or any situation where you need stateful behavior without relying on a full framework. The pattern we built today is used extensively throughout modern JavaScript development. You'll see similar patterns in Vue's composition API, in Sveilt's reactive declarations, and in countless libraries and tools. Understanding the underlying mechanics means you can pick up new tools faster and use them more effectively, because you understand the core concepts they're all built on. This kind of architectural understanding is what employers look for in senior developers. Anyone can use a framework's API, but understanding why the API is designed that way, what problems it solves, and how to implement similar patterns yourself, that's the difference maker. You can apply these concepts in job interviews when discussing state management, in architecture discussions when designing new features, or in code reviews when evaluating different approaches to solving problems. And that's a wrap for our deep dive into custom hooks in vanilla JavaScript. If you found it useful, please like and subscribe to ITower for more in-depth technical content. Your support helps us keep creating detailed explorations and lets other developers find content beyond surface-level tutorials. Drop a comment below if you have questions or want to see us build something specific. Thanks for watching, and see you in the next video.